Hello and welcome to Civil Engineering Mathematics A, Program 8. My name is Eric Tune. I'm a lecturer in mathematics at Central TAFE. In this last program of the series, we'll have a look at trigonometry. Now, trigonometry is one of those subjects that combines algebra with geometry. In the previous program, we looked at analytic geometry, where we did exactly the same. Well, in this subject, we look at triangles, because that's what trigonometry refers to. Trigonometry means the geometry of triangles. But that's what it is at an elementary level. When you look at a more advanced level, then trigonometry becomes very, very important. You can think of wavelengths, simple harmonic motions. You can think of problems involving finding drilling angles in 3 dimensions. And trigonometry is used in all sorts of technical professions. So to have a good knowledge of trigonometry is very, very important. But in this program we keep everything quite simple. Let's have a look what is exactly in this program. We start off with a revision of the theorem of Pythagoras, because you can't do trigonometry without that. Then we look at the basic trigonometric ratios. Then we look at problems that involve finding the angle size. And then we solve right-angled triangles. And lastly, we have a look at practical problems. Well, let's make a start with the theorem of Pythagoras. We did that, of course, in an earlier program, in fact in program 1, where we've got a right angle triangle and we know the hypotenuse, and we know that if we square the 2 other sides, add them up, then we get the square of the hypotenuse. Let's revise that. So here we've got the right angle triangle, we've got the hypotenuse there being the longest side, always opposite the right angle. And indeed that's where it says if we square the 2 sides there, AC and BA, we add up the squares, we get the square on the hypotenuse, BC squared. Sometimes that's written as A squared equals B squared plus C squared, because we call that side A, little a, because it's opposite angle big A. Let's go straight into a problem. Here we need to find the length of the hypotenuse. See, the 2 sides are given, 3 and 5, but we have to find the hypotenuse. So we square 3 and we square 5, add those up, 9 and 25 makes 34. Then to get the value of the hypotenuse, we have to take the square root out of 34 and round that to 2 decimal places. 5.83, correct units, centimeters. The next problem, a little bit more difficult. Here we actually know that the hypotenuse is 5.2 kilometers. The other side is 2.4. We have to find the third. This is actually a matter of subtraction. We actually subtract 2.4 squared from 5.2 squared. I've written that in this particular format with brackets and the square root sign. In the calculator I get 4.613. Now I've actually given it to 3 decimal places because the answer is in kilometers, and we were asked to give it to the nearest meter, and of course there are 1,000 meters in 1 kilometer. Now these problems can become quite difficult. In trigonometry you have to have a good knowledge of Pythagoras, so let's do one more problem on Pythagoras, a little bit more difficult. In this particular problem, we are given that AB equals BC, so those 2 sides are the same. This particular hypotenuse in the small triangle is 5, while the hypotenuse in the big triangle ADC is 8 meters. Now, let's first of all call AB x, and then we can get from Pythagoras that dA squared should be the square of 5 minus x squared. In other words, also, of course, dA squared in the big triangle becomes 8 squared, subtract 2x, all squared. And here's where your knowledge of algebra becomes important, because you should know that 2x all squared is actually equal to 4x squared. So I've got the same thing as I had on the previous graphic, and we equate, because both these expressions are equal to dA squared. So I get 25 minus x squared equals 64 minus 2x all squared, which is 4x squared. Then you solve this, it's an equation, and we get 3x squared to be 39, x squared to be equal to 13, and from that we should get finally that dA then becomes 25, see that's the 5 squared minus the x squared, which we found to be 13, so it's 25 minus 13, and that becomes 3.5 meters, which you may want to check on your calculator. Well, let's make a start with trigonometry. When you work with trigonometry, you always talk about an adjacent side and an opposite side, but it depends what angle you consider before you can call something an opposite side or an adjacent side. I've got that here on the computer. If I've got an angle C over there, then I can call that, of course, the hypotenuse BC, because it's opposite the right angle. That will always stay the same. Now, for that particular angle C, this side, AC, is called the adjacent side because it's next to the angle. The other side there, BA, is called the opposite side. Now, it's important. That is for angle C. If I had considered angle B, then opposite and adjacent would be reversed. Very important. Now, these terms, adjacent and opposite, are used in deriving the trigonometric ratios. You also need to know something about similar triangles. So just a little bit of revision from program 3. In similar triangles, we know that corresponding angles are equal and that the ratio of corresponding sides are equal as well. This is a typical situation where we've got two triangles that are similar. Triangle ABE and triangle ACD. And that's what's written down here. And that's the symbol we use for similarity. Now, if then these two triangles are similar, then there are particular ratios that are equal. And the first ratio I'm considering is the ratio BE over AE. Now, for angle A, that side was called the opposite, remember, and AE is actually called the hypotenuse. But that ratio, opposite over hypotenuse, is exactly the same in the big triangle. So we can also see that CD over AD must be equal to BE over AE. Now, that particular ratio, the opposite of the angle A over the hypotenuse, is called the sine of angle A. And that's normally written as sine A and written as SIN rather than the full word SINE. So we say the sine of A is equal to the opposite of A divided by the hypotenuse. Now there are, if you work it out, 6 of those ratios. Now we will only use 3. It's the sine, the cosine and the tangent, but in higher mathematics you certainly use the other ratios as well. Let's quickly go through the cosine and the tangent in similar fashion to this sine ratio. In this particular cosine ratio, we know that AB over AE, in other words the adjacent over the hypotenuse in the small triangle, must be the same as the adjacent over the hypotenuse in the big triangle. So it must be the same as AC over AD. Adjacent of A divided by hypotenuse of A, that is actually then always the same for angle A. It's called the cosine of A, or abbreviated cos A. And that's how we say it, the cos of A. Similarly for tangent. The tangent is defined as opposite over adjacent. Let's have a look. BE over AB, that is opposite over adjacent, is the same, that ratio, in the small triangle as it is in the big triangle. CD over AC. That is written down here, opposite of A over the adjacent of A. That is called the tangent of A, abbreviated tan A. Now, there are then 3 of those ratios, sine, cosine and tangent. Generally, we use the tangent a lot in engineering problems. Now, when we come back, we'll have a look at some practical problems on how to find angles and also side length using those ratios. Let's now have a look at some problems involving these ratios, and one of them would be to actually get the ratio from a particular triangle. Example coming up. Here we've got a triangle XYZ. We've got this side to be 8, that side to be 6, and that one we don't know, that's x. But of course we can calculate that using Pythagoras. First calculate x, that must be 6 squared plus 8 squared, which is equal to 10, if you take the square root out of 36 plus 64. So we know that one to be 10. What do we have to find? The cosine of y. The cosine is the adjacent side over the hypotenuse. So we should get 6 over 10, 0.6. And for the tangent of z, the second answer, we actually have to get 6 over 8, because we want for z the opposite over the adjacent, 6 divided by 8, and that can be written as 0.75. Let's go straight into a second problem, a little bit more difficult. Here you're asked to draw an equilateral triangle to determine the exact value of the sine of 30 degrees and the cosine of 60 degrees. Those two actually have exact equivalence. Here I've got the equilateral triangle. I've made those sides 1. And when I draw the perpendicular bisector in this, then that side length there is 0.5. So looking at this right angle triangle here, we can see that that angle must be 60 degrees and that angle must be half of 60, which is 30. So if I want to know the sine of 30, then I look in relation to this angle, I take the opposite and I divide by the hypotenuse. In other words, we get the sine of 30 degrees to be 0.5 on 1, and of course that's 0.5. Now similarly, for the cosine of 60 degrees, there's the 60 degrees, but the cosine of course is adjacent over hypotenuse. See, here we've got the 60 degree angle, and so the cosine of 60 then is also 0.5 on 1, or 0.5. In fact, the cosine is called that way because it's the sine of the complementary angle. Complementary, CO, that's where that CO comes from, complementary. Most angles don't have exact values, and you have to get the value from a calculator. In the olden days we used to use tables, but now of course we've got these beautiful calculators, and all of those scientific calculators will have these buttons there, sine, cos and tangent. So if you have to calculate, say, the sine of 40 degrees, then you just press in sine, then the 40 degrees, and you press is equal, and presto, you've got your answer. Some problems on the screen. So here we have to find to 4 decimal places the sine of 46 and the cos and the tangent of those angles. Now you have to make sure that your calculator is in what is called the degree mode, but that is the default mode. And then you just press sine 46, press is equal, and you get your answer rounded to 4 decimal places. And you want to check that at home. The cos of 60.75 degrees, would be no problems there at all. You just use the decimal point, 0.75. And we notice that, by the way, it's very close to the cos of 60, which we previously found to be a half. Now, the tangent of 18 degrees, 12 minutes and 56 seconds need to be pressed in by using the minute and the second button on the calculator. And you might want to go to your instruction manual, pretty easy to find. The answer then becomes 0.3291. Now, quite frequently we know a particular ratio and we want to know from what angle it comes. Then you have to use what is called the inverse trig ratio. Let's have a look at the screen where that is explained. So knowing the value of the ratio uniquely determines the angle. Let's take an example with the sine of A being equal to 0.5. Then we know that angle A must be 30 degrees. Now how is that written? It's written with this inverse notation. There's a little -1 there as a power, and we actually pronounce it as inverse sine. So we would say in this case inverse sine of 0.5 equals 30 degrees. Some books use other notations, like one book might use arc sine, and that's how that is pronounced, arc sine 0.5. I don't particularly like that notation. There's another one, inverse sine. That's sometimes the way that is written. But I like this notation because that's the one that's used on the calculator. Now where exactly is that inverse key? Well, to access it you have to press the inverse button there, or sometimes called the shift button. So if I wanted to get, for instance, inverse sine 0.5, I would press the shift button first, then go to the sine key, press in 0.5, press is equal, and I'll get 30 degrees. Now on the screen I've got some more difficult examples, but basically it is entering the numbers and using the inverse sine or cos or tangent key, and then press is equal. So let's have a look. Here in this example we have to find the inverse sine of 0.8 to the nearest degree. Let's do that one first. I press it in on the calculator. You will get 53.130 and a lot of other decimal places. You round it to the nearest degree, becomes 53 degrees. For the tangent, inverse tangent, so it's a shift tangent key, put in 0.7333 and it comes up with this decimal equivalent of degrees, minutes and seconds. That is equal to 36 degrees, and to convert this you again have to use the degree, minute and second button on your calculator. And I say have a look at your manual and see how that needs to be done, because it can be quite different for different calculators. Let's now have a look how we can use these inverse ratios in practical problems. I've got a triangle problem here and I want you to find the angle. There we've got triangle x, y, z, and we want to find the size of the smallest acute angle correct to the nearest minute. Well, the smallest angle will always occur opposite the smallest side. So being the longest side there, that is side 8. So obviously the angle we want is z, angle z. For angle z, we know that the tangent is 6 divided by 8, because the tangent is opposite over adjacent. So that will be written down here. We've got the smallest angle being z. The tangent of z is equal to 0.75. Then we have to use the inverse tangent. And if we press inverse tangent 0.75, we get 36 degrees and 52 minutes, because we have to get it to the nearest minute. Let's now have a small break, and when we come back we have a look how we can use these ratios in practical problems. Right, in this section we'll have a look at solving triangles, and we also have a look at what's called the angle of elevation and angle of depression. First of all, solving triangle. Well, what we mean by solving a triangle is that we have to find all remaining angles and all remaining side lengths. It's written up here. So in this particular triangle what we want to find is that side A and the angle A there, and also side B, the hypotenuse. That's written up here as well. Length A and B need to be found, and angle A needs to be found. Let's actually do this problem and solve this triangle. So here we've got the same triangle with the same angle size there, 25, and the same length there, 10. How do we go about it? Well, first of all we can find the size of angle A, which must be 65 degrees, because those two angles must add up to 90 degrees. Then we have a look at the tangent ratio, because the tangent ratio is the opposite over the adjacent. If I call the adjacent A, I get tangent 25 equals 10 over A, and that can give me A equals 10 over the tangent of 25 by simple solution to an equation. In the calculator, 21.45. It remains then to find the hypotenuse, and of course we can use Pythagoras for that, and the answer there becomes 23.66 meters. Let's go into the second problem. Here we've got a triangle with two sides given, but we don't know anything about these angles. Again, we use trigonometry. First of all, we want to find the remaining side there by subtraction using Pythagoras. We get I squared equals 18 squared minus 12 squared, which becomes 180. Then I is the square root of that, 13.42, correct units, millimeters. How can we find one of the angles? Well, I've used the sine of angle P, which is opposite 12 over the hypotenuse 18, 0.6667. So we need to find the inverse sine of 0.6667, and on the calculator press shift sign to give me an angle of 41 degrees and 41.81 degrees. Then of course we know that angle Q must be the difference between that angle and 90 degrees, equals 48.19 degrees. Other problems we deal with in trigonometry are angles involving elevation and depression. Now, what are angles of elevation and depression? There's a nice diagram on the screen now. We look at an angle of elevation as the angle that an observer makes when he stands over here and he looks up from the horizontal. It's this particular angle we are interested in. That is called the angle of elevation. Now let's have a look at the angle of depression. That is measured from the horizontal as well. If you stand, for instance, on top of this lighthouse here and you look at that ship, then the angle that is formed from the horizontal to your line of sight, that is called the angle of depression. With angle of elevation and depression, a lot of errors are made, especially with the angle of depression. I've got two problems for you, one involving a tree and the other one involving a cliff. Let's have a look at problem one. Here we've got a tree and you stand 20 meters from that tree and you look up and you see that angle of 35 degrees. You see the top of the tree at 35 degrees. Let t be the height. Then I know for this angle that the opposite is the height of the tree t, the adjacent is 20, tangent 35 equals t on 20, cross multiply the 20 by the tangent of 35, so the t then becomes 20 times the tangent of 35 and that equals 14 meters. Now in problem 2 we are standing on a 35-meter cliff and we observe an angle of depression when we look at the ship of 15 degrees. How far is the ship from shore? Now here's the mistake, because a lot of people, they regard that angle there to be 15 degrees, but that's not the case. This one is 15 degrees, but you can make use of properties of parallel lines to conclude that that angle there is 15 degrees. And then we know that the tangent again of 15 degrees must be 35 divided by d. Consequently, d must be equal to 35 divided by the tangent of 15, and that should come to 130.62 meters. We conclude this program with a physics problem. In fact, it involves statics and forces. In this problem, we have a force of 54 newtons that is applied at an angle of 27 degrees. You want to know what the vertical direction is of that force, because you probably know that forces consist of a vertical and a horizontal component. Drawing the diagram, we see 27 degrees there for the angle, we see the force of 54 newtons there, and we let x be the vertical force. That means that we're looking at a sine ratio, because x is the opposite of angle 27, and we know the hypotenuse. Solving sine 27 degrees equals x over 54 means that x is equal to 54 times the sine of 27 degrees, and that equals 24.5. Well, that is the last problem we will be covering in this particular series. Rather sad occasion. You should of course practice a lot of problems from your book, and I'll give you some directions where to find those. Now, what did we cover in this program? We looked at the Pythagoras theorem, did some revision. We looked at basic trigonometric ratios. Then we found an angle size using inverse trig ratios. Then we solved right angle triangles, and we looked at angles of elevation and depression. And finally we looked at one practical problem. I didn't have time to do any more. Now, as usual, you should try to do some work from your book. The work we are covering in this particular program is covered in the book in chapter 9. It's also called Introduction to Trigonometry. Before we finish, let's recap what we've covered in this subject. In program 1 we covered measurement and mensuration, and by the way, you see these numbers AAB, they refer to nationally recognized mathematics modules. In the second program we continued with measurement and mensuration. We looked at volumes, you may recall, and we made a start with the introduction to geometry. Simple things like what type of angle is an acute angle, a lot of definitions. In program 3 we looked at geometry of triangles and quadrilaterals. That's got to do with similar triangles, an important topic. And then we did algebra. In program 4, 5 and 6 it's all algebra, very important in engineering. In program 6 we also then introduced formula, transposition and evaluation. In program 7 it was the straight line coordinate geometry, quite an interesting topic. I hope you found it interesting. And in program 8, the one just finished, we looked at introduction to trigonometry. Finally, I'd like to remind you of the website that's available for enrolled students. Well, I hope you found this series of interest. I wish you a lot of success with your future studies. Bye for now.